Today we're talking about section 5.4, the fundamental theorem of calculus. It's even in the name that it's a fundamental theorem. It's an important one, and this one shows up everywhere. So we're going to talk about what is the fundamental theorem of calculus and how do we use it to help us with integration. So the fundamental theorem of calculus is broken up into two parts. Part one is the part that everybody always forgets about and find it crazy difficult, but it's really, really quite simple. So it says if f is continuous on a closed interval from a to b, then the function capital F of x, when you see capital F, we're talking about an antiderivative. We're working backwards. So capital F of x equals the integral from a to x of f of t dt. And it says it has a derivative at every point x in that interval. So if I were to do the derivative of f, this is the common sense part. If I do the derivative of the antiderivative, we end up with just the function. So a couple things I want to point out. They've got a t in here, but here there's an x. They're doing this derivative with respect to t. So this is called a dummy variable. And I want you to even write that in there. This is a dummy variable. So we're doing this with respect to x, and this a value is some number, and honestly, if you look at it, it doesn't matter at all what that a value is, because when we do the derivative of a constant, we just get 0. So that's part one, and then part two, we're going to talk about how we actually evaluate. We do the antiderivative at b minus the antiderivative at a, but this video, we're going to concentrate on just part one. So how do we use part one? So this first example says we're going to find the derivative of these two integrals. So the definition said do the derivative of the antiderivative and you get the function. So here I want to do the derivative of the integral of cosine of t dt. So derivative of an antiderivative is just the function. It really is that simple, and I'm going to prove it to you in just a moment. So now same thing over here, derivative of this integral, 0 to x, again, it doesn't matter what this number is, 1 over 1 plus t squared dt is just 1 over 1 plus x squared. Now, I want to show you how this actually works. When we do the derivative of an integral, let's start with just looking at this integral, the antiderivative of cosine. We've done that problem before. The derivative of what is equal to cosine of x? Well, we know that that's sine of x. Derivative of sine is cosine. So the antiderivative of cosine is sine. And this is where that part two comes into play from when I'm proving this. So the antiderivative is sine of t, and we want to evaluate this from negative pi to x. So if I do that, I get sine of x minus sine of negative pi. Now, I'm going to just leave it just like that because this says now find the derivative of all of that. So if I do the derivative of sine of x minus sine of negative pi, derivative of sine is cosine of x, and derivative of a number is just 0. That just proves that part one works. You do not have to do anything fancy. I could do the same thing over here, but I'm hoping you trust me on that one now. Where things get a little bit crazy is when it's not just a plain old x up here. Notice this one has an x squared up in the top. So this is where we have to do a chain rule. Now we've got a function inside of another function. So if I'm going to do the derivative of y with respect to x, I'm going to have to rewrite this to be from 1 to u of cosine of t dt. Now it's going to work out in my favor, except I have this u work here. U was x squared. So if we were to do a chain rule problem here, we would say the inside function was x squared, and the outside function was integral from 1 to u of cosine of t dt. So when we do chain rule, derivative of the inside function, and then the derivative of this one with respect to u, remember t is just a dummy variable, and what we learned up here was if I'm doing derivative of an integral, it's just the function at this point. So we're going to get cosine of u. Now what do I do with these two pieces? I have to multiply those. So I get 2x cosine of, and we replace the u with x squared. Ta-da! So in example 3, now we notice that we've got the x on the bottom and the number on top. That doesn't work for us. We have to have the x up on top for part 1 to work. So if I'm going to find the derivative, I want to flip-flop those. Well, good thing that in one of our previous lessons we learned we can just flip-flop those two. But in order to do that, we have to make the integral negative. So now to find the derivative of an integral is just the function, but this time it is negative. So we would have negative 3x sine of x. In part B, this one gets a little bit more complicated because now I've got an x on the bottom and I've got an x on the top. So what I want you to think about is if you have kind of this number line, they're talking about from 2x to x squared. Now I'm going to say, let's start this number line at 0. I want this region here from 2x to x squared. I'm going to have to write this as two integrals. So I'm going to say, well, what if I go from 0 to x squared and I take away 0 to 2x? That would leave me with 2x to x squared. So let me write that out. The integral from 0 to x squared of 1 over 2 plus e to the t minus the integral 0 to 2x, 1 over 2 plus e to the t dt. Now what I hope you realize is neither one of these is just plain x. So I've got two chain rules here. So I'm going to hit this one first. The inside function is x squared, and the outside function is the integral from 1 to u of 2 plus e to the t dt. So the derivative of x squared was 2x. And derivative of the integral, 1 over 2 plus e to the u. So I need to multiply those two pieces together. So I get 2x over 2 plus e to the x squared. Now that was just this first one. Minus, now we've got this one up here. I'm going to use u again. This time u is 2x. 1 to u of 1 over 2 plus e to the t. So the derivative here is 2. Derivative here, 1 over 2 plus e to the u. Multiply those together. 2 over 2 plus e to the 2x. So there is the derivative of that integral.